Section 3.9. The last section in Chapter 3 is called differentials. Oops. Here's a function. Change the window a little bit. What function is that? That's the sine function. What I want to do is I want to find the equation of the tangent line of the sine function at x equals 0. So how would I find the equation of the tangent line of that function at x equals 0? Take the derivative. All right, so our function is f of x equals sine x, and I want the tangent line at x equals 0. So I take the derivative, f prime of x. So the derivative of sine is cosine x. Then what do? No, I don't set it equal to 0. I plug in 0 for x to find the slope of the tangent line. So the slope of the tangent line is f prime at 0, which is cosine of 0. Cosine of 0 is 1. Okay. So now I can use y minus y1 equals m times x minus x1. Y minus, what's my y1 value? 0, because I take 0, plug it into my original function, sine of 0 is 0, equals m was 1 times x minus 0. So that's just a fancy way of writing y equals x. Okay, so there's the graph of the original function. And there's the graph of y equals x. What can you tell me about those two graphs?
Well, they run on that line, they run the same. Like, the slope of the like, how to explain it, but it's the same.
It's not the same, but it's very close to the same. I think what you're trying to say is, it looks like from right about here to right about there, those two functions are almost the same, aren't they? Pretty close. Let's zoom in a little bit and see. Zoom in right at 0. So there's your sine wave, and there's your derivative function. Are those two functions almost the same for a while? Yeah, they're very close, aren't they? I'll zoom in even a little more. And as I zoom in more, there's the sine wave. The sine wave, as I zoom in more and more, looks more and more like a straight line. And so there, it's difficult to tell where the sine wave is and where the tangent line is. And if I look at my window, I'm going from x equals minus 0.38 to x equals 0.38. So I get a very small window there. That's the whole idea behind differentials. The idea behind differentials is you can approximate a curve using a line. And which line do we use to approximate the curve? The tangent line. You can approximate a curve by its tangent line for small values now I forgot what I was going to say. Small values in the change in x. That's not a very good sentence. What I mean by that is, here's my curve again, and here's my tangent line. Do my curve and my tangent line look almost the same? Well, they do for a little while, right? If I asked you, x is pi over 2, and I asked you to estimate this curve with the tangent line for x equals pi over 2, would you have a very good estimation?
Yeah.
No, I don't think so. Because sine of pi over 2 is 0, and on our tangent line, if x is pi over 2, y is Well, it's not even close to 0, is it? It's up like at 4 or something. It's pi over 2, correct. Because our line is y equals x. So when is the tangent line a good estimation for this curve? Where the tangent line is. And real close to that tangent line. It looked very, very good when I zoomed in, correct? Right, but again, not perfect. So x could go from maybe, I don't know what our window is here. The window goes all the way to 1.5. So if this is all the way to 1.5, it looks like it's a pretty good estimation for x up to a half and x as far down as minus a half. But it would not be a good estimation if x were 4, for example. 4 is too far away from 0 to be a good approximation. All right, so we're going to have a bunch of symbols here. I'm just going to draw a couple. It's easiest to describe the symbols in a picture. So I'll draw the sine wave again. So there's the sine wave roughly, and here is our tangent line at 0. Okay, so we found the tangent line at 0 in this case. So I'm going to call that x0. I'm going to call that point x0. Our tangent line will be a good approximation for values that are pretty close to 0. So I'm going to call that point right there, that value, I'm going to call that x1. And this distance right here is called delta x. So the distance from where you found your tangent line to where you want to approximate, that distance is called delta x. Okay? Good so far? All right. If I plug delta x into the original blue curve, and if I plug x1 into the original blue curve, and I plug x1 into the tangent line, will I have exactly the same answer? No, but it'll be close, won't it? Okay? So I plug x1 into the original curve, into the tangent line, that would be f at x1. And I plug x1 into the original curve. What to call that?
I thought it was f of x. That's 1, and that's f prime, right?
Well, it's not f prime. It's the derivative. It's the tangent line. I'll call it L at x1 because it's the equation of the tangent line at x1. So if the delta x value is small, then the change in those two things should be small. If we call this one delta x, then what should we call that one?
Delta y.
That should be called delta y. All right, so list of symbols here. Delta x is x1 minus x0. And delta y is f at x1 minus line at x1. So those are the exact changes in x and the exact changes in y. All right, now what I want to do is I actually want to figure out the equation of my tangent line. So if I have some function f of x, how do I find the equation of the tangent line? I take the derivative. So dy dx would be f prime at x. And then I'm going to do this. I'm going to write this as dy equals f prime at x dx. What did I do there?
You just rearrange the equation.
I just rearranged the equation. All I did is I moved the dx over to the other side. Okay. What's dx?
Change in x.
It's still the change in x. dx is exactly the same as delta x. But now what's dy? F prime at x dx.
It's when you multiply the derivative and delta x together.
You multiply the value of the derivative times the change in x. And what does that give you? It doesn't give you delta y. But it gives you something very, very close to delta y. So dy is f prime of x dx, which is going to be very close to delta y. And this is called, right here, this is called the differential approximation. All right, so let's do a specific example here. Give me a function you like. Anybody got a function they like? I don't want it to be a line. Because what's the tangent line to a line?
A line.
It's the exact same thing. It doesn't change anything.
2x squared plus
2x squared plus 7. Okay? And we need a base point. x0 is going to be 2. And then x1 is going to be some point that's pretty close to 2. So give me a number that's pretty close to 2. 2.5. All right, so x0 is 2, x1 is 2.5. So what would delta x be? 2.5 minus 2, which is 0.5. And what would dx be? Exactly the same thing. Delta x and dx are always equal to exactly the same thing. Okay. What would delta y be? No, that's dy. dy would be f prime of x dx. What's delta y?
Difference in f of x1, f of x, yeah.
Okay, so delta y is the exact change in y. So I take 2.5, I plug it into the original formula, and I take 2 and plug it into the original formula, and I subtract those two values. And that tells me exactly how much y really changed. So that's going to be 2 times 2.5 squared plus 7 minus 2 times 2 squared plus 7. That gives me the exact change in how much y changed. Let's see, I grab my calculator. 2 times 2.5 squared plus 7 minus 2 times 2 squared plus 7. That turns out to be 4.5.
Wait, I thought you said that you plugged the second one into the derivative.
Did I?
You said the line, which is the tangent line, which is the derivative.
Well, for delta,
Oh, you're right, I did. I messed up. I'm sorry.
Which one is it?
Delta y should be the change in y. So delta y should actually be that much. That one's delta y. So delta y is f at x1 minus f at x0. You're right, I did screw that one up.
Okay, it was a discrepancy.
Well, it was a mistake. You're absolutely correct. Delta y is the true amount the y value actually changed.
So is the delta y that you put beforehand actually dy?
Yes, that one should have really been dy.
Okay. Okay, that makes more sense. I got it.
All right, so
It's okay. It's a Friday before break.
thank you. Okay, so what this tells me is if I take 2.5 and plug it into this original formula and take 2 and plug it into this original formula, they differ by quite a bit, 4.5. All right, so now let's find out what dy is. dy is f prime of x delta x. So what's f prime of x? 4x dx. Now I take and I plug in 2. So if I plug in 2, I get 4 times 2 times delta x is a half. What's 4 times 2 times a half? 4. So is my dy close to my delta y? Kind of close. Are they real close? No, not in this case, but they're kind of close. All right. Let's try another one. How about y equals?
Is that really only three?
For now. There'll be more in a minute. Be patient. Y equals. How about we do 3x cubed minus 5x squared plus 2. And x0 is going to be, what are we going to use for a starting value?
0.
I don't like 0.
Dang it.
5. And my x1 is going to be 5.01. We'll make them real close. Now, if I gave you a choice, your choices are, you can take this function and you can plug in 5, or you can take this function and plug in 5.01, and you're not allowed to use your calculator. Which one would you prefer to do? You'd prefer to plug 5 in. How come? Because it would be a lot easier, right? Okay. Now I'm going to give you a choice. You can take 5.01 and plug it into this original formula, or you can take 5 and plug it into this differential formula. Which one would you pick? The differential one. How come? It's a lot easier. All right, so let's do that. Let's figure out dy first this time. So dy would be 9 times 25 minus 50 times, how much is dx? 0.01. What's 9 times 25? What's 225 minus 50? What's 175 times 0.01? It just moves the decimal place 2 positions. This is 1.75. Okay? With me so far? All right. Now let's go back. Let's plug 5 into the original problem. So y at 5 is, I plug 5 in, I get 3 times 125 minus 5 times 25 plus 2. How much is 3 times 125? 375. 375 minus 50. I'm sorry, that's not 50. What the heck am I thinking? 125. It's 250 plus 2. 252. Okay? Good so far?
Yes.
All right. So how much is y at 5.01? Approximately? It's near 252. How far off? It's off by about 1.75. So y at 5.01 should be close to 253.75. Because it's positive, so we would go bigger. Correct. For this problem? Well, no, I have one more question. How good an answer is this really?
Horrible.
Horrible? Let's see. 3 times 5.01 cubed minus 5 times 5.01 squared plus 2. The exact answer, y at 5.01, is 253.754003. So how good was our linear approximation?
Pretty darn.
Pretty accurate. Accurate to 2 decimal places, wasn't it? Questions on that? Yeah, I'm not done. I'm not done. Just getting warmed up.
Question, how does this get harder?
How does this get harder?
Bigger numbers, no calculator.
Bigger numbers, no calculator, that certainly makes it harder. I don't think it really gets any harder. Well, we'll see in a minute. We'll see in just a minute. So, let me ask you a question. Why would I want to go through this process? Why wouldn't I just want to take my calculator and type in 5.01 right from the beginning and work it out? Why would I want to do this sort of approximation? What's that? So we know the math behind what? The calculator. That's correct. This is another one of those examples that's a little bit archaic, that people don't do this anymore. Again, before the time when people had calculators, this was very important. This was a way for them to approximate functions quite accurately, quite quickly. The reality is today, this doesn't happen a whole lot. But again, it's an example of how your calculator works. Does your calculator use a linear approximation? Probably not, because according to the linear approximation, the answer should be 253.75. The calculator was able to do better than that. So how does your calculator work?
Advanced algorithm version of it.
No, not really.
It actually sort of like solves it. 5.01 is easy for it to square and cube and all that.
Okay, that's really not very difficult for the calculator, I would agree. So how does the calculator do sine of pi over 7? Magic. Probably not. What you will learn next semester when you take Calc 2 is that any function
Oh, is this the square thing?
Nope.
The box thing?
Nope. Any function that has derivatives can be approximated by a polynomial.
Oh.
No, this is a preview of what you'll do next semester.
I see factorials and I'm already...
And it could go on and on and on. So what you will learn in Calc 2, you'll learn something called Taylor series and Maclaurin series, or Taylor polynomials and Maclaurin polynomials, named after the two famous dead guys who came up with these things. But what you learn is that any polynomial can be, or any function can be approximated by a polynomial. Any function that has derivatives anyway. Anytime you can find the first derivative, second derivative, third derivative, you can approximate it with a polynomial.
And is that the polynomial that they use every time? Or is that just happen to be the one you came up with?
No, that happens to be the polynomial for sine. And there's a similar one for cosine, there's one for e, there's one for ln. All those functions can be written as polynomials.
See, e and ln are not my biggest fans. E is great for derivatives. I love that one.
Yes, e is when you take Calc 2 and you learn to take the derivative of e to the x, you will like it very much. The derivative of e to the x is
E to the x.
e to the x. It's its own derivative. That's an odd one. Strange one.
It makes change.
Anyway, so what we did, what we've done so far is we did the linear approximation. So what we learned today is that sine x is not equal to x, but sine x is
Close to x.
almost equal to x as long as your x numbers are pretty small, as long as your values are close to 0. This polynomial works even when x is a big number. The more terms you have, the more accurate it's going to be. So, unfortunately, my opinion is this section is in the wrong place. I really wish we did this section in Calc 2, where first we would do linear approximations, and then the very next day you would do polynomial approximations, and it would make a lot more sense. And that's what's happening with your calculator. Your calculator does not have a sign stored into it. It's got a function that approximates sine. So when you type sine of pi over 7, it's actually giving you an approximation, a very accurate one. It's probably accurate to 7 or 8 decimal places, but it's very accurate. Questions on that?
Why do you, I understand you guys teaching us the history lessons just to know how to do it, but why do you teach them like randomly in the middle of the book, not like all the history lessons beforehand? Like, we don't use this stuff anymore, but like this is kind of something.
Well,
Why isn't it its own kind of thing? Why is it kind of shoved in the middle of a different chord? Like, it just feels out of place.
Yeah, I agree somewhat. Part of the answer is I can't teach you about Newton's method and differentials until you know about derivatives. So I couldn't have done it at the beginning of the semester because you didn't know what derivatives were. Wouldn't have made any sense. So I kind of have to do it here. Like I say, I truly think this section on linear approximation belongs in Calc 2. But every book in the world that I've ever seen puts it here because it's an example of how to use the first derivative. All right, so other things you can do with differentials. Approximate. The square root of 9.2. And I think you were looking at the take-home review. I think it adds square root of 81 point something. I forget what it was. 81.6. All right. If I'm going to approximate the square root of 9.2, and I'm going to use differentials, I need a function. What function should I be working with if I want to estimate the square root of 9.2? Nope. What function do I use to approximate the square root of something? What function do I use? The square root function. So there's the function I'm going to use. I need to pick up my base number. The number you want a number close to 9.2, but you want a number that's real easy to plug into your original function. 9 is a real easy number to plug into that original function, isn't it? And then the x1 would be 9.2. Correct. So what's dx in this case? 0.2. All right, so the change in y is approximately equal to dy, which is f prime of x dx. What's the derivative? 1/2 x to the negative 1/2 dx. So it's 1 over 2 square root of x dx. I agree completely that negative 1/2 drops to the bottom, becomes a square root. All right, so the correct change in y is approximately dy, which is, now I plug in my numbers. So for my x number, what am I going to plug in? 9. So that's going to be 1 over 2 square roots of 9 times dx. dx is 0.2. So that's 1 over 6 times 0.2. It's how much? 1 over 30. How'd you get 1 over 30? 0.2 is 1 over 5. So that's 1/30. All right, so final answer. How much is the square root of 9.2? It's about 3 and 1/30. Because we know the square root of 9 is 3, so the square root of 9.2 has to be a little bit bigger. How much bigger? About 1/30.
So the value we throw in, if you give us approximate a number, you want us to throw that number in as the x1, and the easy number is always is the 0.
Correct.
Okay.
Yeah, your base number is always the easy number. The easy number to plug in. Well, let's just see how good that was. Square root of 9.2.
Could you tell us how much that 30 is?
So how close are they? Pretty good. Accurate to 3 decimal places.
Where does 3 come from? Square root of 9.
Square root of 9 is 3. So the square root of 9.2 has to be close to 3. How close? It should be about 1/30 away. All right. Last sort of question you'll see in this section. A piece of paper is cut to be 11 inches by 8.5 inches. This piece of paper in front of me, is it exactly 8.5 by 11? No, why not? How? There's no instrument that can cut things exact and be correct, exactly correct all the time, are there? No such instruments exist. So when I say this piece of paper is 8.5 by 11, is it exactly 8.5 by 11?
Close enough.
But it's close, okay. So the tool used to cut it was accurate to within, how close do you think it was?
0.001.
0.001 inches. Use differentials to approximate the error in computing the area of this sheet of paper. What should the area of this sheet of paper be? If the instrument cut it exactly correctly, what should the area be? 8.5 by 11. So the area should be 93.5 square inches. So the area is probably very, very close to 93.5 inches. The question is, how far off could it possibly be? So how do you find area? Length times width. So now I want to find how much my area could be off. How much my area could be off, that's dA. That's the change in area. How do I find the derivative on the right-hand side? I have to use the product rule. Why do I have to use the product rule? Two variables being multiplied together. So I leave the first one alone. That's L. And I take the derivative of W. What's the derivative of W? Not dW over dA. It's 1 dW. It's very, very much like when we did implicit differentiation. Whenever you take the derivative of a something, you're going to have a d something. Plus, then I leave the W alone, and I take the derivative of L. What's the derivative of L? dL.
We don't have to put over A.
Nope. You're not taking the derivative with respect to A.
Okay. What is the difference? That I'm confused.
What's the difference? Before, our underlying variable when we did these, we might have written dA dt, because our underlying variable was always time. What we have here is we have area written as a function of L and W. So when I take the derivative, I'm really doing dA over dL, and I'm also doing dA over dW. Except we're choosing to write the dL and the dW over on this side.
Yeah.
Okay, we're choosing to kind of do a multiply it to the other side sort of thing. Okay? All right, so our change in A. How far could the area be off? What's L? 8.5. And what's dW? Not 11. 0.001. Plus, what's W? 11. And what's dL? 0.001. So our area could be off, and usually we would do this even. Our area could be off by plus or minus 0.0195 square inches. Why do I put plus or minus?
Because it could be either too long.
The machine might have cut the piece of paper too long. The machine might have cut the piece of paper too short. I don't know which way it cut it. Could be off either way. Questions on that? The other question you would be asked with this is, what is the percent error? How do you find percent error? Anybody know? You do what?
The theoretical value, what it should be, subtract what you got, the absolute value of that, and then divide it by what you should have got, and multiply by that.
Okay, so you take what you should have gotten, which is 93.5, minus how much it could be off. Absolute, well, that's going to be a positive number anyway, but you're right, you would do absolute value of that. Then you divide by the original, and you multiply by 100%.
I thought the second one had to be the value of it, though.
I don't think your formula is right, because according to your formula, our error is 99.97%.
So that would be like correct.
No, it's
It's
just, you have to take 93.5 and add the 0.0195 to it, and then subtract it from 93.5. You take the actual, you take the accepted value, which is 93.5, minus the value that you would have gotten, so you have to add the error in. Then you have to divide it by the accepted value, and then multiply by it.
Okay, so I think you're right. I think this tells you how accurate it is. It's 99.7% accurate, but that's not what we wanted. I think the formula for percent error is you simply take how much you're off, divide by what it should be, and multiply by 100%, which is exactly what you just said.
I just said it more complicated, yeah.
So our estimation of the area is only off by 0.02%, which is very, very small. Which is not surprising because we said our machine was really quite accurate. 0.001 inches was our original error. Okay, so why would people care about things like this?
Because if it's not really inaccurate, then we get a bunch of big wasting paper.
Building.
Okay, you could be wasting paper. I don't think we're too concerned about wasting paper. What sort of things might we be concerned with?
He said building.
Building what? Yeah, this is really in a physics area or an engineering area, this is called tolerance. And so when you build things, depending on how closely they need to mesh, how closely they need to fit together, you need to know how far your error is. And one of the best examples I can think of is if you're building a car and you want that piston to slide up and down inside the cylinder, what has to happen? It's a very, very tight fit. Why does that have to be a very, very tight fit? And if it doesn't fit tightly enough, stuff's going to leak out. And that's when your engine has gone bad and you have lots of problems with it. So that's the example. That's the sort of thing that people are looking at when they're looking at percent errors and things, tolerances. If you're building a car, that piston needs to fit in the cylinder, but not quite touch, right? It's got to be within a very, very small amount. So you need to know that your machine is accurate enough to cut the cylinder out correctly, and your machine is accurate enough to cut the piston correctly, so that the two things, the tolerances will be close enough, the things will slide and work correctly. Okay? That still is used. Approximating errors using differentials is still used in some places. I've seen some engineers tell me they do still use that. Questions?
I'm still not understanding how, back to the approximating the root of 9.2, I still don't understand the answer.
The answer? All right, well, we know the square root of 9.2 should be close to the square root of 9, right? But how far off are they? Well, if I were to take square root of 9.2 minus square root of 9, by definition, that would be our delta y. That's the exact change in y. But delta y is very close to what? dy. Which we figured out to be 1 over 30. So look what we have. We have square root of 9.2 minus square root of 9 is really close to 1 over 30. So if I want to know what the square root of 9.2 is, what do? Add square root of 9 to both sides. So the square root of 9.2 is approximately square root of 9 plus 1 over 30, which is 3 plus 1 over 30. So that's really what I did. I skipped several steps there. I probably should have written those in.
Oh, I thought the answer was 3, 1 over 30, not 3 plus.
Right. Yeah, so that's strange notation in math. 3 plus 1 over 30 is the same as 3 and 1/30th. We're not multiplying 3 times 1/30 there. That's mixed numbers are strange notation in math. They look like multiplication, but they're not. Other questions?